We see in a planar graph. What is meant by planar graph? The graph which is drawn on the plane, there is no any intersection between the edges. That graph is called as a planar graph. So in case of planar graph, we can find out number of vertices or number of edges or number of regions if any two values is available. So first you should know what is meant by region in case of planar graph. So region is nothing but area which is surrounded by the edges, group of edges, that is called as a region. So if you consider this graph, in this case regions are, this is one region, this is second region, and plus one, that is outer region, it is also considered. So there are three regions in case of this graph. If you consider this second graph, in this case there are 1, 2, 3 and plus 1, that is 4 regions are there. You know about vertices and edges. So in any planar graph, if they provide any two entities, then you can find out the third entity by using this Euler formula. So what is this Euler formula? It gives V minus E plus R is equal to 2. So here V is equal to number of vertices, then E is equal to number of edges, and R is equal to number of region. So this theorem 1 related with this, if G means graph G which is contain V comma E, set of vertex and set of edges, is a simple connected planar graph, then E is always lesser than equal to 3V minus 6. And theorem 2 says that E is lesser than is equal to 2V minus 4. Otherwise, if the graph is a simple and it is connected planar graph, then number of edges are always lesser than equal to 3V minus 6. Otherwise, means if it is not simple, in that case number of edges is always lesser than equal to 2V minus 4. Examples: K5, K6 and K3 are a planar. So you have to find out whether these given graphs are planar graph or not. This is nothing but K5 means it is complete graph with 5 vertices, it is complete graph with 6 vertices, and it is complete graph. So it is a bipartite, complete bipartite graph K33, and you have to check whether it is planar or not. So you have to check there should not be any intersection between the edges. If this condition is satisfied, then we can say that this is the planar graph, otherwise not. Now we'll see some operation on the graph. So we can perform a different operation on the graph. So first, union. So we seen a union operation in the set theory. Same, but just see, if G1 is a graph with V1 set of vertices and E1 set of edges, and G2 is a graph with V2 comma E2, means V2 is a set of vertices and E2 is a set of edges. These are the two graphs. Then union, that is resultant graph G3, is equal to G1 union G2, whose vertex set is V3 is equal to V1 union V2, and edge set E3 is equal to E1 union E2. Means resultant graph G3 will contain vertex set V3 and edge set E3, which is union of V1 union V2, and edge set E3 is union of E1 union E2. So see the example. So this graph is G1, this second graph is G2. So it contains vertices, G1 graph contains vertices V1, V2, V3 and V4, and G2 graph contains vertices V1, V2, V4 and V5. So these two vertices set we will make a union. So these vertices will get added in the resultant, that is V3 set. So V3 will be added, and in case of edges, these two edges will be newly added in the resultant edge set, that is E3. So result of union of two graphs G1 union G2 will be this graph. It contains all the vertices. Only the common repeated vertices is appear only once, and it is also the union of all the edges. Next operation that we can perform on the graph is intersection of two graphs. So if there are two graphs G1 V1 comma E1 and G2 V2 comma E2, then intersection G3 is G intersection G2. So this is the symbol of intersection. So just this is intersection, whose vertex set is V3 is equal to V1 intersection V2, and edge set is E3, which is obtained by intersection of E1 intersection E2. So same graph we taken as an example, G1 and G2. So intersection of G1 and G2 will give this result. In intersection, we know that we seen in the set theory, we are taking only the common terms. So in case of vertices, we will take common vertices between the G1 and G2, and these vertices are V1, V2 and V4. And also we will take a common edges, and these edges are A and D. So this resultant of intersection of two graphs G1 and G2 will give this graph. Ring sum. So next operation that we can perform on this graph is ring sum. In a ring sum, if G1 is a graph with vertex set V1 and E1, E1 is edge set and G2 is V2 comma E2 are the two graphs, then ring sum, that is G3 is equal to G1, this symmetric operation, symmetric symmetric difference G1 G2, whose vertex set is V3 is equal to V1 symmetric difference V2, and edge set E3 is equal to E1 symmetric difference E2. So we also see in the symmetric different operation. So in this case, we know that how we can obtain symmetric difference of two set. So it is nothing but set 1 union set 2 minus set 1 intersection set 2. So that is nothing but symmetric difference. So in graph G1 and G2, we know that the union of G1 and G2, it will contain all these vertices along with this, and it also contain A, B, C, D edges along with E, H. So in previous operation, this is nothing but the union of these two graphs, and then intersection of these two graphs is also be aware with intersection, that is nothing but this. Now symmetric difference, we stated that we union means G1 union G2 minus G1 intersection G2. So now we also aware with the difference, it will contain all the element from set 1 except element which is present in the set 2. So in this case, we have to exclude the edges only which is exist in the intersection of G1 and G2. So this is the result of G1 symmetric difference G2, that is the ring sum. Then complement of a graph G denoted by G dash is the graph whose vertex set are same as the vertex set of G, but two vertices are adjacent if they are not adjacent in G. Means if this is the original given graph G, so in case of complement of this graph, it will contain all the vertices from the given original graph, but edge in case of edges, the edge will be exist in the complement of that graph if that edges, you can see that, but two vertices are adjacent if they are not adjacent in G. adjacent edge, you aware with that what is meant by the adjacent vertices, the vertices which connected with the same edge, so that is called as the adjacent vertices. So in this case you can see that we taken only those edges which not exist in the original graph. Then complement of a complete graph is always a null graph. So we know that in a complete graph, in case of complete graph, all vertices are connected with all other vertices in the graph. That's why there is no such edge exist which is present in the original graph and not present in the complement graph. So because of that, complement of complete graph is always a null graph. Self-complementary graph. If it is isomorphic to its complement, then it is called as a self-complement graph. Self-complementary graph means we aware with what is meant by isomorphic. Isomorphic means three conditions should be satisfied. Number of vertices should be equal to the means both graphs should have equal number of vertices, then equal number of edges, and then equal means degree also matching of the vertices. Then it is called as a means adjacency should be matched. Then it is called as a isomorphic graph. So if we obtain the graph after the complement of the original graph, and if it is isomorphic with the original graph, then it is called as a self-complementary graph. Now last term from this lecture, that is handshaking lemma. So handshaking lemma states that the sum of the degree of all vertices in a graph G is twice the number of edges. So we know that in case of a directed graph, degree in number of edges incident on particular vertices are nothing but the degree of that particular vertices. So in handshaking lemma means when you suppose you make a handshake with any person, so the persons are considered as the vertices, and you are shaking the hand with the person. Suppose you shake hand with the one person, then your degree will be 1. So the sum of degree of all vertices. So it stated that sum of degree of all vertices. So if you shake a hand with one person, then the degree of these two vertices will be 2. So whatever number of edges exist in the graph, then degree of all the vertices will be 2 into that particular edges. So you can see here, we summation of degree of vertices is equal to 2 into mod of E, or summation of degree of Vi, means Vi means 1 by 1 they taken, summation of dVi is equal to 2E, where I is equal to 1 to n. N is nothing but total number of edges from the given graph. So this will be helpful for finding the degree summation of degree of all the vertices in the given graph.